For nearly 3 decades, the sheltered water of the Hashirajima Fleet anchorage in Japan's inland sea near Kure held the wreckage in a cold stasis. Between 1943 and 1970, the site changed from a fresh wound into a geological feature of the seabed. While the surface world moved on from the war, the battleship Mutsu remained exactly where she had fallen, hidden beneath a blanket of silt and time. When the Fukada Salvage Company finally arrived to assess the site, they were not looking at a ship in the traditional sense. They were looking at a chaotic debris field scattered across the ocean floor at roughly 40 meters, about 130 feet. The environment at this depth is deceptive. 130 feet is technically within the range of standard diving, but the conditions in the anchorage were hostile to human vision. The seabed here is composed of soft, distinct clay and mud. Any movement by a diver or a current stirs up this sediment, reducing visibility to near zero. The salvage engineers could not simply look down and see the battleship. They had to feel for it in the dark, mapping the broken giant by touch and by sonar. What they found was a study in the physics of stability failure. The explosion in the No. 3 magazine had done more than just sever the hull, it had violently altered the center of gravity for the remaining sections. A battleship is an inherently top-heavy structure. It carries massive weight high above the waterline in the form of heavy gun turrets, armored conning towers, and superstructures. When the hull is intact, this weight is counteracted by the buoyancy of the hull volume below the waterline, creating a positive righting arm that keeps the ship upright. However, when the bow section was severed from the rest of the ship, that delicate balance was destroyed. The center of buoyancy shifted instantly while the center of gravity remained high. The righting arm vanished. Gravity took over, and the massive weight of the upper works pulled the hull over. This is why the divers were dealing with the roughly 150-meter forward section. It capsized to starboard and sank almost immediately after the No. 3 magazine explosion. On the bottom, the forward wreck was not a clean hull form, but a collapsed geometry driven into soft sediment. The stern section presented a different geometry. The 45-meter stern section upended and remained afloat for hours before sinking at about 02 hours on 9 June. It came to rest a few hundred feet south of the main wreck. The two halves of the ship lay close to each other, but their orientations were radically different. This meant that any salvage plan would need to account for two completely different extraction strategies. One section had to be lifted from the bottom up, while the other was effectively nailed to the floor by its own inverted superstructure. Hanging over this engineering challenge was the dark history of the sinking itself. The IJN investigation concluded that the explosion was the work of a disgruntled crew member. That conclusion has been argued over ever since, but it meant the site carried the procedural feel of an investigation, not just a recovery job. The divers were not just entering a salvage site, they were entering a crime scene that had been frozen for 30 years. While the truth of Hatanaka's guilt remains a matter of historical debate, the possibility that human malice rather than mechanical failure had caused the disaster made the wreck feel different from other war graves. It was a place of unresolved conflict. The physical condition of the steel was the final constraint. After 30 years in salt water, the metal had begun to corrode, but the thick armor plate of a battleship does not rust away quickly. The hull was still structurally sound enough to be lifted, but it was also heavy enough to kill. The divers moving through the gloom had to navigate jagged edges of torn steel that were as sharp as razors. They were crawling inside a collapsed mountain of iron where a single mistake could trap them or sever their airlines. To recover the evidence, and the steel engineers would have to dismantle a capsized mountain of metal in zero visibility. Disassembling a battleship underwater is not a demolition job. It is a process of reverse construction performed in a hostile environment. When the Fukada Salvage Company arrived on site in 1970, they faced a geometry problem of immense proportions. They could not simply pack the hull with explosives and blow it to pieces. That would scatter the steel and destroy the value of the scrap. Instead, they needed to surgically remove massive sections of the ship and bring them to the surface intact. To do this, they had to devise a cutting plan that ignored the conventional rules of marine salvage. The primary challenge was the armor. Mutsu was built to resist 16-inch naval gunfire. Her belt armor and internal bulkheads were thick, hardened steel designed to defeat high-velocity projectiles. Standard underwater cutting torches, which rely on a diver manually burning through metal with oxygen and electricity, were functionally useless here. The visibility was too poor and the steel was too thick. A diver working in zero visibility mud could never maintain the precise line needed to slice through a hull of this magnitude. The engineers needed a method that could cut through armor plate, teak decking, and internal wiring all at once without requiring a human hand to guide the blade. The solution they employed was a technique known as the chrysanthemum cut. This is a method that relies on friction rather than heat. The salvagers threaded heavy steel cables underneath the hull sections and looped them back to winches on the surface barges. By pulling the cables back and forth in a sawing motion, they created a giant flexible friction saw. The cable bit into the ship, grinding its way through the keel, the armor plate, and the internal compartments. It was a brutal but effective mechanical strategy. The cable did not care what it was cutting. It simply eroded a path through the battleship, separating the steel into manageable blocks. However, deciding where to place these cuts required a deep understanding of structural continuity. A ship is essentially a box girder, a long, hollow beam that derives its strength from its frames and longitudinal stringers. When you cut a ship into sections, you are destroying that continuity. If you place the cut in the wrong location, the section you are trying to lift will lose its rigidity and fold in on itself like a crushed can. The engineers had to identify the strong points of the hull, specifically the heavy transverse frames that held the shape of the vessel. The plan required slicing the hull into blocks that retained enough of this internal framing to stay rigid during the lift. If they cut midway between two frames, the plating would have no support. When the crane applied tension, the steel would buckle and tear. The engineers mapped the hull using the original blueprints and the tactile surveys from the divers, aligning their wire saws with the heavy structural bulkheads. They were effectively slicing a loaf of bread, but they had to ensure that each slice was thick enough to support its own weight without crumbling. This was particularly critical for the inverted bow section. Because it was upside down, the structural logic of the ship was reversed. The keel, which is the spine of the ship, was now at the top of the stack. The salvagers used explosive-shaped charges to make precise incisions where the wire saws could not reach, specifically on the thickest parts of the propeller shafts and the heavy machinery spaces. These charges were not designed to destroy, but to separate. They snapped the steel connections with surgical precision, leaving clean edges for the lift. Throughout this process, the team had to constantly account for the center of gravity of each individual block. As the wire saws severed the connections, the stability of the wreckage changed. A section that had been supported by the rest of the hull was suddenly free. If the engineers miscalculated the balance, the multi-hundred-ton block could shift or roll over in the mud, crushing the divers or snapping the cutting cables. Every cut was a calculated risk that altered the equilibrium of the wreck site. By the time the cutting phase was nearing completion, the battleship had been transformed from a single coherent wreck into a series of independent heavy lifts. The bow and stern were no longer monolithic failures, but collections of engineered targets waiting for extraction. The cuts were plotted and the cables were run. The separation was complete, but identifying the blocks was one thing, lifting them was another matter entirely. The engineers had sliced up the mountain, but now they needed a machine that could pick up the pieces without snapping the crane boom or sinking the barge. The machine selected to conquer the wreck of the Mutsu was a floating leviathan with a lift capacity of 1,500 tons. In the world of marine salvage, numbers of this magnitude represent a hard ceiling. If the load exceeds the rating of the crane, the steel cables do not simply stretch, they detonate with the force of a high-caliber gunshot. The Fukada Salvage Company had brought their heavy-lift crane ship to the anchorage, but the margin for error was razor-thin. They were attempting to lift components that pushed the engineering limits of the era. The economic logic behind this extreme effort was driven by a unique property of the steel itself. The Mutsu was constructed long before the first atomic bomb was detonated in 1945. This meant her hull was forged from low-background steel, free from the radioactive isotopes that contaminated the atmosphere and the global steel supply during the nuclear age. In the 1970s, this pre-atomic steel was a critical resource for sensitive medical instruments and Geiger counters. The wreck was not just a pile of scrap, it was a mine of radiologically pure iron. This value justified the risk of the lift, but it did not change the physics of the operation. To move this precious metal from the seabed to the surface, the engineers had to master the concept of the load path. In structural engineering, a load path is the specific direction that force travels through a system. When a crane lifts a sunken object, gravity pulls the object down while the crane pulls it up. The tension travels from the object into the rigging shackles, then up the wire rope over the sheave wheels of the crane boom, and finally down into the hull of the crane ship itself. Every inch of this path must be unbroken. If the shackle is too small, the load path breaks at the connection. If the wire rope has a kink, the load path breaks at the cable. If the crane barge does not have enough displacement to counter the weight, the entire vessel tips over. The engineers had to calculate the load path for every single lift, ensuring that the force was distributed evenly. A single point of failure would result in the load plummeting back to the bottom, potentially dragging the crane ship down with it. The most critical test of this system was the preparation for lifting turret number 4. This component weighed approximately 1,000 tons. Unlike a hull section, which could be slung with cables passed underneath a gun turret, is a dense, compact mass of armor and machinery. There is nothing to wrap a cable around. The engineers had to drill into the armor plate and weld massive steel lugs directly onto the turret structure. These lugs became the start of the load path. This created a terrifying dependency on the quality of the welds. The divers had to weld these attachment points underwater in zero-visibility mud. If the weld had a porosity defect or a crack, the lug would shear off the moment the crane took the strain. The entire weight of the 1,000-ton turret would hang on these few points of contact. It was a gamble on the skill of the underwater welders. There was also the issue of dynamic loading. The 1,500-ton capacity of the crane was a static rating, meaning it applied to a load that was hanging perfectly still. But the ocean is never still. Even in the protected anchorage of Hashirajima, small waves and swells caused the crane barge to heave up and down. If the barge rose on a swell while the load was fixed to the bottom, the sudden snap tension in the cable could spike the load well past the safe working limit. This is the difference between holding a weight in your hand and jerking it upward. The dynamic shock can snap a cable instantly. The salvage team had to wait for a perfect weather window. The rigging was heavy and complex, involving thick wire ropes that hummed in the current. The divers connected the massive shackles to the welded lugs on the turret. The slack was taken up slowly. The cables tightened, shifting from a curve to a straight line of steel tension. The load path was established. The crane began to apply force pulling against the weight of the battleship. The rig was ready and the physics were aligned, but the sea floor held onto the steel with a force that gravity alone could not explain. The crane operator watched the tension gauges climb past the theoretical weight of the load. According to the blueprints and the salvage calculations, turret number 4 should have weighed approximately 1,000 tons. The 1,500-ton crane had the capacity to handle this mass, but the gauge was telling a different story. The cables were singing under the strain, and the crane barge was beginning to dip lower into the water, yet the turret remained stubbornly fixed to the bottom. The salvage team was running into a phenomenon that kills cranes and snaps cables. This is the physics of breakout force. When a heavy object like a battleship turret sits in soft clay for 30 years, it does not just rest on the surface, it sinks into the sediment, displacing the mud and creating a perfect airtight seal around its base. This changes the lifting equation entirely. To lift the object, you are not just fighting gravity, you are fighting the vacuum pressure of the seabed itself. When the crane pulls upward, it tries to create a void underneath the object. Because the mud seal prevents water from rushing in to fill that space, the water pressure of the ocean pushes down on the object with crushing force. This creates a suction effect that can double the effective weight of the lift. The only way to break this seal is to apply force significantly greater than the weight of the object, or to slowly work the object loose until the water can breach the seal. The engineers had to feather the controls, applying massive tension to the load path without exceeding the breaking strength of the wire ropes. It was a standoff between the hydraulics of the crane and the grip of the clay. For minutes, that must have felt like hours, the barge held the tension. The steel ropes were stretched as tight as piano strings, vibrating in the current. Then, with a sudden shudder that ran through the entire crane ship, the suction failed. The seal broke. Water rushed into the void beneath the turret, and the 1,000-ton assembly popped free from the mud. The load on the crane instantly dropped to the true weight of the steel, but the danger was not over. The sudden release of tension caused the barge to rebound violently, requiring immediate stabilization to prevent the swinging load from smashing into the lifting vessel. Slowly, the prize rose from the darkness. For the first time since 1943, the number 4 turret broke the surface of the Hiroshima Bay. It emerged upside down, a dripping mountain of dark steel covered in marine growth. As it cleared the waterline, thousands of gallons of trapped seawater poured out through the hollow 16-inch gun barrels, creating a waterfall that cascaded back into the sea. The sight was surreal. The massive guns, which had once been trained on the horizon, were now acting as drainage pipes for the dead ship. This success proved the strategy was viable. Fukada's team did not stop with a single lift. Between 1970 and 1978, they cut, separated, and raised major components, including the 2 aft turrets in 1970 and 1971, and ultimately scrapped about 75% of Mutsu, recovering hundreds of remains in the process. The sheer scale of the recovery was an engineering triumph. They had taken a ship that was thought to be lost forever and brought the vast majority of it back to the world of the living. The operation generated thousands of tons of scrap metal and recovered the remains of hundreds of crewmen, fulfilling the dual mandate of commerce and closure. The retrieval of turret number 4 in one piece remains one of the most impressive feats of heavy lift salvage in the 20th century. It demonstrated that with enough steel cable and enough patience, even a 40,000-ton warship could be reversed from the seabed. However, while the operation was a resounding success, not every part of the ship could be saved. The cutting torches and the lifting cables had limits, and as the operation wound down, the engineers had to decide what to leave behind. The turret broke the surface, but the operation left one final question. What happens to the pieces that are too broken to save? The ocean does not negotiate, and eventually it reclaims everything. While the Fukada Salvage Company achieved a massive victory by recovering 75% of the battleship Mutsu, they could not take it all. Today, if you scan the bottom of the Hashirajima anchorage with sonar, you will still find a distinct geometric anomaly rising from the mud. It is a 35-meter, about 115-foot, section running from the bridge structure forward to the vicinity of number 1 turret. The highest portion of that remaining wreck sits about 12 meters below the surface. This remaining section sits in the silence of the deep, subjected to the slow violence of marine chemistry. This is the domain of corrosion and fatigue. In the oxygen, poor environment of the deep mud, steel degrades at a slower rate than it does in the splash zone near the surface, but the process is relentless. It is an electrochemical reaction where the iron atoms are physically stripped from the hull structure, bonding with oxygen to form iron oxide. Over decades, this turns the hardened armor plate into brittle flakes. The structural integrity of the bow is fading. The rivets that hold the plating to the frames are rotting away, and eventually gravity will flatten this final section into an unrecognizable stain of rust on the seabed. However, the parts of the ship that were torn from the grip of the seabed clay have found a second life. The salvage operation was not just a harvest of scrap metal for Geiger counters, it was an act of unintentional preservation. The most visible public relic is the number 4 turret at Etajima, but it was not restored from the seabed. It is Mutsu's original number 4 turret, removed during her interwar refit and placed there as a training aid in the 1930s. The aft turrets raised from the wreck in 1970 and 1971 were ultimately scrapped. It stands there today as a white-painted fortress of steel. It is a jarring sight because it represents a scale of engineering that no longer exists in the modern world. In the 1930s, when Mutsu was refitted, she was defined by her towering pagoda mast, a chaotic skyscraper of bridges and platforms that dominated her profile. That mast is long gone, lost to the explosion and the scrapyard, but the turret remains as an anchor to that era. You can walk up to it and touch the armor that was once buried 130 feet underwater. You can look down the barrels of the 16-inch guns that were once clogged with the silt of the bay. Other pieces of the giant are scattered across Japan. One gun from turret number 3 is displayed in Kure, at the Maritime Museum, popularly known as the Yamato Museum, while the other is displayed in Tokyo at the Museum of Maritime Science in Odaiba. Other recovered components were distributed to memorial sites and museums. These artifacts are clean and dry, far removed from the cold pressure of the anchorage. They serve as a physical connection to the 1,121 men who were lost when the magazine detonated. The site itself remains a war grave, while the salvage operations in the 1970s recovered the remains of many crewmen who had been trapped inside the hull for 30 years. The bow section that remains on the bottom is still a tomb. The Japanese government treats the coordinates with the reverence due to a cemetery. No further salvage is planned. The 115-foot section will remain there until the chemistry of the ocean finishes the job that the explosion started in 1943. The story of the Mutsu is a strange case in the history of naval disasters. Most shipwrecks are binary. They are either lost forever in the dark or they are afloat and preserved. Mutsu is both. She is a ship that was destroyed by a mysterious explosion, partially resurrected by an audacious engineering feat, and now exists in two worlds. Part of her stands in the sunlight as a monument to naval power, and part of her rots in the darkness as a monument to the finality of death. The salvage engineers proved that they could defeat the suction of the mud and the weight of the steel, but they also proved that you can never truly bring a ship back from the dead. You can only recover the pieces.